Hi everyone, I would like to welcome all of you to Frontline Systems webinar on an overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am Consulting Lead and Modeling Specialist at Frontline Solvers. During the presentation, if you have any questions or comments, please type them into the chat box to be answered at the end as time allows. I strive to remain within the promised time frame, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the optimization applications are widely used across many industries and functional areas: energy and utility, chemical, manufacturing, transportation, agriculture, financial services, and government. These are just some of the examples, and some of the functional areas: staff planning, scheduling, routing, blending, capacity planning, product mix, portfolio optimization, and so on. We would like you to know that many of our customers have found optimal solutions for their large-scale industrial problems worth millions in savings, as building a model can give you insights and a money-saving optimal solution. Today, we explore how optimization can benefit you in solving your business problems and how easy it is to use our tools to solve them. Together, we'll review typical applications in transportation, inventory management, financial services, scheduling, staff, and one example of automating optimization using VBA. Maybe you wonder what solvers are good for. So let's start talking about the decision-making process and using optimization to solve a problem. It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be your money, equipment, staff time, transportation fleet, or raw materials inventory. All of these are resources and they are allocated for some purpose. For example, deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. Portfolio optimization is another example. It is about allocating money to stocks in a portfolio. And scheduling is really a matter of allocating people to time slots or scheduling the availability of hospital operating rooms. Solvers or optimizers are software tools that help you determine the best way to allocate those resources. What do you need to use a solver and how do you define your optimization model? Let's drill down on this further. There are three main steps that are determining your decision variables, objective function, and constraints. Each optimization problem involves one or more decisions that must be made in order to solve the problem. The decision variables are typically numbers, reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. These decisions need to be made in the best possible way while simultaneously satisfying a number of logical conditions or constraints. Constraints reflect the physical situations, and there are various types of them. Some of the constraints represent limits on available resources such as inventory or money. There are some of them that reflect the physical situation. For example, non-negativity on variables. You cannot produce a negative number of products. You cannot assign a negative number of people to tasks. And some constraints are determined by policies that you or your organization may set. For example, In a portfolio optimization, you might have a limit on the maximum percentage of funds to be invested in any one stock or one industry group. And then you might have balance constraints. For example, warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in. These kind of constraints have an equality form. Another example, beginning inventory of this cycle equals the ending inventory of last cycle. That's another kind of balance constraint. And then another common element in each optimization problem is the existence of some goal or objective that the decision maker considers when deciding which course of action is best. You can determine the objective function with asking, what measures are we trying to optimize? The best or optimal solution might mean maximizing your profits, minimizing costs, or achieving the best possible quality. Now, it is time to dive in and see how we can solve a problem in practice. In this example, we are just going to review different kind of constraints in a typical application, so don't worry about all the details. We are going to, in the next couple of examples, review the optimization models and then define an optimization model from scratch together. Transportation and logistic operations of your company can be a competitive differentiator. So, in this example, we are going to find out how optimization can be used to optimize a typical transportation operation. So, this is about a company that has 3 different goods that have to be shipped from 2 factories to 4 warehouses, and from those warehouses to the 5 customers, or directly from factories to the customers with minimum cost. This is at the right side, the diagram of the system with nodes for factories, warehouses, and customers. Now, I need to show the supply-demand pairs, displaying feasible routes for the shipment plan. I'm going to use these gold color arrows to show you the potential flows from factories to warehouses and customers, and then these green arrows to show the potential flows from warehouses to customers. The amount of product that is going to be shipped on each of these routes is under your control. This is what we call decision variables. And we will reserve one cell for each of these routes in Excel. And we are going to review that together in a second. So let me switch to Excel. You can see the full Analytics Solver platform ribbon. Analytics Solver platform is a comprehensive product that includes optimization, simulation, and also data mining and text mining, and time series forecasting in the Excel Miner platform component. Today we are just going to focus on the subset of ASP called Premium Solver Platform. This product will only include the optimization component. So let's change the product, and I will show you how to do it. So if you have a trial version, you can do this yourself. Click on Help, and the first option is Change Product. Instead of Analytics Solver Platform, let's check Premium Solver Platform and click OK. It's going to load now. Let's click on the ribbon. And now we only have access to optimization. Let's skim through the ribbon together because we're going to use it in the examples. First is the Model tab. As you can see, clicking on the Model tab displays or hides this task pane on the right side. In the Model tab drop-down, there are additional options for multidimensional modeling that are beyond the scope here, and you find examples and more information in a user guide. Optimization Model tab allows you to set up your optimization model. As you recall, each optimization model has 3 components: decisions, constraints, and objective. And in your objective function, either you want to minimize something or maximize, like minimize your cost or maximize your profit. Then you have parameters tab, providing you with the options to run multiple parameterized optimizations, and we are going to use that today. With Solve Action tab, you just click on this button to solve your optimization models. Then in the Analysis tab, here you can analyze the results using different reports and charts. Tools tab enables you to examine optimization results. And there's this Publish button that allows you to publish your models for use and distribution on the web. And with that we mean Excel Online and Google Sheets. And then there's this Get Data. Get Data allows you to summarize from big data. This means you can bring in your input parameter data that you would use to drive an optimization model. For example, if you have millions and millions of sales orders in a large database across different hard disks, you are not going to use every single order in your optimization model. With this facility, you can get a sum or average based on region or gender, or even a sample. Therefore, if you have huge volume of data somewhere, you can use this feature to analyze it using the familiar Excel interface and build your optimization model. And then here we have options to set options for optimization charts and graph, and then Help tab. Here you can display online help, use live chat, control guided mode, which we will discuss in more detail today. You can open examples and access user guides and the user guide, reference guides, and you can check your online, license status and more. Now let's review the task pane together. Model tab allows you to view the model in outline form. You can see the results of model diagnosis and optionally edit model elements in place down here. Platform tab is next. Here you can view or change the platform options such as the number of optimization to run, and you will see how you can use this option, or default bounds on your decision variables. And then Engine tab. Here you can select a solver engine and then set its options. And then Output tab allows you to view a log of solution messages or a chart of the objective value. Now back to our example. Let me put it back onto Model tab. As you can see here in this Excel workbook, the cost of shipping from factories to warehouses, factories to customers directly, and from warehouses to customers are recorded here in these cells. These are inputs to the problem that are not under our control. These shipping costs are quoted to us by our outside shipping company, for example. What is under our control are decisions about how much to ship along each route at these different locations. So we need to reserve cells for variables representing quantity shipped from factories to warehouses, factories to customers directly, and from warehouses to customers. So you can see that these are the cells we have reserved for factories to warehouses, factories to customers directly, and then warehouses to customers. And just to prevent any confusion, here we have used name ranges. So what a name range means, you just select, for example, as a block of cells, and you would define a name for it in Excel. Just enter a name like column I, and then this set of cells, if you use them, instead of referring to the range, our software can recognize the name, and this is helpful if you want to summarize. Just to clarify why we have these names here. So in regards to decision variables, you can see that all these blocks are defined as decision variables, and then in the next couple of examples I will show you how you can define decision variables. So we have these three blocks of decision variables for the amounts to ship from factories to warehouses, customers, and warehouses to customers. Now, what measure are we trying to optimize? Each route of flow incurs a cost. So we have two goals that need to be carefully addressed in this problem: total cost and the service. We want to provide the service with minimum cost and ensure that each customer demand is completely satisfied. The objective function is here in cell C91. I just double clicked from the model tab on total cost, C91. Let's click OK and review the formula in C91 together. As you can see, it is represented by a sum product function. For example, the first component. To calculate total cost of shipping from factories to warehouses, since the cost coefficient for these routes are defined in cells C10 through F15, we need to multiply these by total amount of product that will be determined to be shipped, our decision variables for which we have reserved cells C41 through F46. And then similarly, we need to add other cost components. Now on to different constraints that we have for this transportation problem. What restrictions limit our choice of decision variables? The capacity of each warehouse, supplies available from each factory, and the demand from each customer needs to be considered. So here are warehouse capacity constraints. We want to make sure that what we ship into the warehouses doesn't exceed the capacity of those warehouses. We cannot overload the warehouses, as each one has a physical capacity. So ship to warehouses, here we are calculating what is shipped to each warehouse, and then it should be less than warehouse capacity for each of the warehouses. Then we have a certain supply available at each factory provided in these cells H63 through H68. The total flow from factory 1 for each product type must be smaller than or equal to the factory supply, and this is the same for factory 2. Then we need to ensure that each customer product demand is satisfied, and here are these constraints. Total to customers should be greater than the demand. So again, let me show you that if I select this block, I just named it demand. That's why it is appearing as demand here. And then the last set of constraints. Warehouses are temporary holding points, therefore flow out from one warehouse is equal to its flowing. Again, these are called balance constraints. And as you can see, they have equality form. Total to warehouse equal total from warehouse. Okay, for now, let's just go ahead and solve the model by clicking the Optimize button on the ribbon. I'm clicking on this light bulb on the ribbon. This time, we are going to step our way through guided mode and see what it can tell us. This feature is a guide offering help for you in each step of your modeling efforts, preventing common errors. For example, let's click Continue, and you can see two things happen here. First, Solver has analyzed all the formulas in this model and determined the structure of our model automatically. It is a linear programming convex. It's just linear program is a type of optimization models. And then, because the right solver engine wasn't selected, it is letting us know and giving us other choices. So I am going to choose the right solver engine, which is recommended to me, which is standard LP quadratic. And my choice was not recommended. And this is just based on structure of your optimization model. LP is a linear model, and we have an LP convex model, so we should better use the LP solver. This is a better solver to solve this problem rather than LSGRG, which is a solver for nonlinear type problems. But even if without knowing all of this information, this guided mode can help us choose the right solver engine. Now let's click on next step. Solver found a solution. All constraints and optimality conditions are satisfied. Now if I click OK, we get the solution. So here's our solution. We achieved what we wanted here, which was to determine how best to ship products between their factories, warehouses, and customers. So these are the amounts to ship from factories to warehouses directly, and then from factories to customers directly, and then from warehouses to customers. And then with these amounts, we are going to minimize our shipping cost, which is now going to be $519,700. So imagine you have used this guided mode for a while and you're solving over and over. So you might to get rid of all these dialogues that you have to click through every time. So let me show you how you can make this change here. Click on Help, Operating Mode, and if you want to change this guided mode, you can switch to Auto Help mode. It is better than Expert mode because Expert mode eliminates all the help, but Auto Help mode will just bring the dialogues when there is a problem. So that's what recommended if you don't want to use this guided mode. We just looked at how optimization can help us with a typical transportation problem, and you saw that how we can define different types of constraints to see all the situation, all the limitations that you have on this shipment plan. Now, let's look at an inventory management example. This is about a warehouse that sells 4 products with a different demand for each product. As you can see, each of these 4 products has a different holding cost and requires a certain amount of space. And as you can see here, we have a limited storage capacity. So, what is the best ordering policy for a warehouse to minimize cost while meeting demands? As you might know, there is an analytical solution for this problem, which is known as the economic order quantity, or EOQ. Unfortunately, this formula doesn't always work in the real world. Demand usually fluctuates, ordering time is variable, and other factors arise to further complicate the problem. In this model, we have one such factor, a limited storage space. So we have reserved these cells for the variables. And as you can see, I've used the name range quantities for this block of cells. These variables are the amounts to order each month for each product. And then you can see that these are defined on the variables in the optimization on the variables quantities. By changing these variables, we change the total cost. And you can see total cost is calculated in this cell E17, which is sum of cost for each of product. And if I show you one of the components, you can see that this cost is calculated by this formula. Holding cost times average inventory level plus the cost to place an order times average number of orders. So it's just following the EOQ formulas. And then we have one constraint, storage capacity constraint. The space used should be less than available space. So it's in G17, and then should be less than available space in G6. And you can see this is the sum for all the space used for all the products, and this is calculated by the product average inventory level times the storage space per unit. This is a nonlinear type problem based on the formulas. And I'm going to hit the solve button and you will see that solver would automatically identify that for us, and we need to use a nonlinear engine. Another thing is that you will see that given this storage limit, the solution will be less than the EOQ formula solution. So let's click on Optimize. Let's click on Continue. As you can see, solver analyzed our model and it diagnosed the model as nonlinear programming, NLP, or non-convex. And let's click on Next Step. And here the message that tells us that solver found the solution, optimal solution. And if I click on Engine tab, you can see that I choose standard LSGRG nonlinear engine. And there is an option for you to choose automatically select engine and allow solver to choose the right engine based on the diagnosis of your model structure. And this is just a solution report. So here are the results. Amounts to order each month, minimizing our cost, meeting demand, and without exceeding storage space. Next, we are going to review an example in a financial services application. This is about allocating money to stocks, and we are going to define this optimization model together from scratch. An investor wants to target a specific rate of return for his portfolio while minimizing risk. Of course, this is a portfolio optimization application. So, the goal is to find the best combination of stocks that minimizes risk for a given return. Let me open the workbook. So you can see in the Model tab, there is no optimization model defined. I'm going to increase the size. As you can see, I have the covariances between all the stocks recorded here. I have the returns for each of stock. And then we are calculating variance, and we are going to review these other sections together: variance, standard deviation, and return, total return. So this is just, I just organized the data and created the formulas under the spreadsheet, and we are going to use them together. So what are the variables? What is under our control? The percentage allocations of the funds that we can invest in each stock. So I reserved cells C14 through G14 to hold the percentage allocations of funds or the decision variables. Again, I named this block of variable cells allocations. So let's define the decision variables together. You have to first select the cells that you want to reserve as your decision variables, then go to Premium Cell Platform ribbon, click on Decisions, and then Normal. And you can see allocations, or this block of variables is defined as our decision variable. Let me just show you. So if we have like a set, I wanted to, for example, this was the row of cells I wanted to define as decision variables. Let me color them. I would just select them, click on Decision. So there's two ways: either just click on Decision and choose Normal, or just click on this button. And you can see this I5 through K5 is defined as decision variable. Now if I want to give it a name like pink, you can see that if I click on refresh the model, you can see that solver recognizes this name range for this block of variables. So let's delete that. So I just wanted to demonstrate how you can define name ranges. Okay, now let's go back to our example. So now we want to define the objective. Our objective here is the portfolio variance. I have defined a quadratic function at cell C18 here to calculate the portfolio variance by custom quad product function. You can see this quad product function. And now to select this as an objective function to be minimized, select the cell C18, click on objective and then minimize. You can see the portfolio variance. Again, this cell has a name range. Portfolio variance will be added as our objective function to be minimized. Now, what are our constraints or limits on our decision variables? We have two constraints. The first is the total portfolio constraint that needs to be 100% or 1. So we need to sum the allocations of funds to stocks and then make sure it will be equal to 100% or 1. In this cell, we need I have a formula that calculates the sum of all portfolios. So you can see sum of C14 through G14, sum of all allocations. And then I want to define a constraint, making sure this total or sum of all allocations is equal to 1 or 100%. So select this cell and click on constraints. Now the first one is constraint again. So this one, I want to make sure it is equal to 100%. So I need an equality constraint. So I'm going to use the second one. Total portfolio, which is H14, you can see H14 is highlighted, need to be equal to 100% or 1. So for the right hand side of this constraint, I'm going to enter 1, or you could enter 100%. And then click OK. You can see this constraint is added. We have another constraint. The total portfolio return must be greater than 9.5%. So we have to calculate the total portfolio return in one cell and then make sure we add a constraint to force the solution to be greater than 9.5%, to force the solver to find the solution that gives us that return, that desired return. So I have used this cell, C20, to calculate portfolio return. And you can see the formula. It is a sum product of allocations and the expected returns. So this cell represents the formula. I'm going to select this cell to define it as a constraint. Click on constraints. Constraints. This time we want to make sure our portfolio return is greater than 9.5%, greater than or equal to, so I'm going to choose greater than or equal to sign. So in this add constraint dialog, portfolio return is our left hand side, we have the sign greater than or equal to, and the right hand side, we are going to enter 9.5% and click OK. And you can see that this constraint is added. Another way would be to enter 9.5% in a cell and then point the constraint to that cell. So I'm going to enter 9.5% and show you that you could just use this cell to point to this cell instead of using entering the number. But let's just enter the number for this one. I'm going to delete this value. Okay, so we defined our optimization model. Now we are ready to hit the solve button and get the results. Let's click on optimize. Let's click on continue. Our model was diagnosed as a quadratic programming convex model. Next step, and solver found the solution. All constraints and optimality conditions are satisfied. Here are the allocations of funds to different stocks. You can see the total is 100%, and These allocations of funds to stock achieves the 9.5% return, our desired return. And it has the minimum variance or minimum risk. So this is often called an efficient portfolio. You may have heard of the efficient frontier. Using premium solver, we can construct that efficient frontier rather easily. Let me show you how. So far, in our example, we have used the solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Let's generalize that. We can utilize parametric optimization to find the efficient frontier. That is the optimal solution for several levels of portfolio return. So the portfolio return, the several levels of portfolio return, will be our parameter, and we are going to define a lower and upper bound for it. For example, we are going to check different return levels from 8% to 14% and solve the optimization models for all of those. So to do this, first select an empty cell, for example D20. Let's change the color to red, okay, yellow. And then click on Premium Solve Platform, click on Parameters, Optimization. Now I'm going to insert a parameter in this cell, D20. You can see in the function argument we have a lower and upper and base case value. We're just going to enter 8% for the lower level and 14% for the upper level. And the reason is one of our stocks returns, oh, what did I do? Sorry. Let me correct this, 14%. So you just can correct the formula here, or you could correct it in the model tab here. Parameter, you can see this parameter is added, and the value for lower bound is 8%, and the upper bound is 14%. So there are different ways you can correct this parameter. So 8 and 14, okay. And as I was mentioning to you that the reason we are just going up to 14% is just one of our stocks return 14%. Okay, so this is our parametric return rate. Now we have to modify the constraint that we have. Our portfolio return must be greater than 9.5% for the previous situation. Now instead of this 9.5%, we are going to point to our parametric return rate. So I'm going to click on this button and click on to choose our parametric return rate, D20, and click OK. So you can see our constraint is modified and it's pointing to our parametric return rate. Now next thing we need to do is to change the number of optimization. So let's click on Platform tab. If you recall, the first option is number of optimization to run. It is 1. I'm going to change it to 10. So the solver will run 10 optimization. It would divide that interval between 8% and 14% to 10 different values and then run the optimization for each of them. So we are ready. Let's click on Optimize to solve the problem. And I'm actually showing you how to clear. Using this button, we can clear the output. And let's click on Optimize. I'm going to skip guidance this time and show you that we finished 10 optimization problem, number 1, 2 through 10, and you can see the report in the Output tab. The worksheet will initially display values for the last optimization. These are the optimal values for our allocations for the last optimization. You can see the return is 14%. And the total is 100% as we requested. So to change this and display any of the optimization results, it's very easy. Just go to Tools tab. You can see there's this drop down and it's on optimization 10. You can change it to optimization 1. You can see the return is 8%. based on the parametric return rate. This is the optimization that was solved for the 8% return rate. And you can see the optimized allocations and our portfolio variance. Or we can go to optimization. The second optimization, you can see the return was 8.67, and then different values for our allocations and so on. This is how you can really verify all the optimization results. Now, let's click on charts, multiple optimizations, and monitored cells. Let's choose our objective function, portfolio variance, and click on this button to move it to the right-hand side. I'm just trying to show you how you can have the efficient frontier. And then click OK. This is the efficient frontier plot. Now, to the right side, there's this additional options. Click on this right side button. And here, let's choose the option chart options. So, in the x-axis or x-coordinate, we have the optimization index and then different objective function values, different variance values for the y-coordinate. And we can change the x-coordinate. Instead of showing optimization index, we can show our parametric return rate values. So now you can see the parametric return rate and portfolio variance. So this was how to have the efficient frontier plot for this optimization problem. Let's close this and go back to our slides. This is just a recap on what we practiced, modeling and solving problems in Excel spreadsheets. You can reserve cells to hold the values of your decision variables, and then pick a cell to represent the objective function and enter a formula that calculates the objective function value in that cell. And then pick other cells and use them to enter the formulas that calculate the left-hand side of the constraints. Now, the right-hand side, you can enter them as numbers in other cells or enter them directly in the solver's add constraint dollar. And one quick note, it is best practice to use constants for constraint right-hand side. Now, we are ready to look at some scheduling examples. This is about allocating staff. An amusement park needs a certain number of employees each day of the week. Every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire, and what schedule should they be on to minimize total payroll costs? So let me open the example. For our employees working 5 consecutive days with 2 days off, we are looking to find the schedule which meets the demand from attendance levels and while it is minimizing payroll costs. We have 7 possible schedules with 2 consecutive days off. So here are days off, and here are our 7 possible schedules. We name them A through G. Our decisions reflect the number of people that should be hired for each of the 7 possible schedules. And as these are people, we need integer values, full numbers. So as you can see, we have them as defined as integers. Here, employee per schedule is defined as integer. And employee per schedule is actually the name range for this block of decision variables. How you can define variables as integer? You just select them, go to constraints, second option, variable types or bound, and then define them as integer. You can see it will be added as integer. I'm going to delete one of them. Okay, that's how you define your variables as the integer, full numbers. So this is our total demand that needs to be satisfied. And we have this constraint, employee per day should be greater than required per day, which is our demand. Attendance, required attendance. And there is one more constraint, and that is non-negativity. The number of people cannot be negative, right? So how we did this, you can see it is not here. One way would be for you to select the variables, click on constraints, variable type bound, and define them as greater than or equal to 0. That's one way, so let's add that, but I'm going to remove it because if we go to engine tab, there is an option for assume non-negative, and it is set to true. That's just the same as defining non-negativity for our decision variables. So there are two ways to do it. Okay, now we're ready to hit the optimize to solve this optimization problem. I'm going to skip guidance, get the results quickly. So here are the results, the number of required people for each schedule. 2 people for schedule A, 5 for schedule B, and so on, which minimizes our total payroll cost and it is going to satisfy our demand, as we can see here. So we had the greater than equal to, that's why, like for example, we have 23 here. Now, this park has hired the required employee. Now it needs to decide which employee goes on which schedule. And each employee has given a list with his or her preferences. So in the next workbook, there is another version of this problem. He's trying to solve problem in this situation. How should the park divide the schedules among the employees, given that each employee given a list with his or her preferences, where a 7 means the most desired schedule and 1 means the least desired. And these are here. This information that we have collected from our employee are given here. So we can see employee 1 to 26, and then these are schedules A through G, and these are the preferences of each employee for each of the schedules. You can see employee 1 and 2, both of them prefer schedule F. The most desired schedule for them is F, and least desired, for example, for employee 1 is a schedule G. How to define this optimization problem? So we have reserved these cells as binary variables. Binary variables are used for yes and no type of decisions. So these are all our decision variables. You can see this is called the schedules, this whole block. And you can see this is defined here, the schedules. And you can see the schedule is defined as binary. And to just define the schedules as binary, we select them, go to constraints, variable type bounds, and binary. But what that mean? For example, if we assign schedule F to employee 1, you will see there will be a 1 here instead of 0. That will be our solution. But all the other ones, we want to make sure there are zeros because we want to assign each employee to just one of the schedules. So 1 here means a decision to allocate schedule F to employee number 1. And if I have a 1 here, it means a decision to allocate a schedule E to employee number 4. And then here we calculate the sum of each allocation of schedules to employee 1. For each employee, we have this sum, employee 1, employee 2. And we want to make sure that each employee is allocated to exactly one schedule, right? So we have this constraint here, schedule per employee, which is that block of all the sums for each of the employees should be equal to 1. Just to making sure each employee is assigned to just one of the schedules. Now, our objective is to optimize employee preferences. And in this case, it means maximizing the sum of all preferences. You can see we have these total preferences in cell U50, and we are going to maximize total preference. You can see this is a sum of all preferences. And let me show you, for example, how we calculate the preferences for first employee. We have this sum product function of employee preference values that he has given us and the schedule that is assigned to his employee. So if we assign F to employee 1, schedule F, there would be a 1 here, and that 1 would be times times 7. So we have a 7 for preference value of employee 1, and so on for all other employees. Again, we have just one. We will have only one in each of these blocks because we are making sure that the schedule per employee is 1. So there will not be like 2 ones here, just one. Okay, so we are ready to solve this optimization problem. Let's click on Optimize. I'm going to skip guidance, and you can see the solution. So in the optimal solution to maximize the preferences, you can see that actually schedule B is assigned to employee 1 with a total preference of 6. You can see 1 times 6 is 6. For employee 2, we are assigning schedule C to employee 2. And you can see the total preference for that is 5. And then for the third employee, we are assigning schedule D, and D preference for employee 3 is 7. And by the way, we have this quality constraint that employee schedules must be equal to employee required, and we are satisfying this constraint here. And these are just totals of all these ones. So we want to make sure we have 3 people for schedule A as we determined in the first scheduling problem, and so on. In this model, we solve the problem after finding the solution of scheduling 1. It is also possible to find both solutions automatically. And to do this, you can write a VBA macro. So it's a good time to talk about how you can automate your optimization models. I'm not going to go through a lot of details, but I just want to show you that this is available to you. Either you can just define an optimization model in Excel and run it with VBA and change some of the options, or you can just define a whole optimization model from scratch writing the VBA code. You can do this with our VBA object-oriented API. You can automate your model and control the solver engine. You just define the whole optimization model from scratch. And these are the examples that are available to you. Refinery example and cutting stock. We are going to review the refinery example very quickly together. This is the refinery model. You can see the optimization model is predefined. We're just going to run the model with the macro, call the solver, run the model, and how to retrieve sensitivity information from VBA. Just these are the things that we want to practice seeing how you can define using the VBA. So this problem has a goal to plan the operations of a refinery to maximize total profit. This refinery purchases 2 crude oils and then puts them through 4 processes: distillation, reforming, cracking, and blending to produce petrols and fuels, which are then sold. So you can see decisions again, objective, and all the constraints. The model is defined. Now let's review the VBA code together, and this is the button that we'll use to run the macro. Developer, let's click on Visual Basic. Here's the code. So there are some details about setting engine. I'm going to skip them. What is more important is within problem, as new problem, you create an instance of an optimization problem. So here just all the details about setting up parameters of choosing your solver engine and setting its parameters. But then you can just have prop.solver optimize to run your optimization problem. So within prop as new problem and prop.solver.optimize, you could run this optimization problem with macro. You don't need all of these details, but these are just here to show you how you can do this, how to select the engine, how to set the parameters. And then here we are putting a message box for returning optimization status, and then Then we have the for loops. Here we are returning final decision variable values in the message boxes, and also we have another message box for reduce cost and shadow prices, just how you can retrieve all the solution information. And then here with prop.solver.report, we are asking for an answer report. And you are going to see what happens when we run this macro. So I'm going to close this Visual Basic window and click on Run Macro. We get the optimization status, and the message was as we requested. Then if I quickly click through these boxes, you can see the final variable values, and then you can see the reduced cost as requested in that for loops and shadow prices. And at the end, you can see an answer report is generated for us. Now let's review the different software that are available to our product line. You can access our optimization software within Analytics Solver Platform or Risk Solver Platform product, or get it as a standalone program such as Premium Solver Platform or Premium Solver Pro. Everything we saw today can be done using Premium Solver Pro or more advanced products, subject to your model size. These Solver upgrade products have very nice usability features with limits related to your problem size, structure, and solver engines. Platform products allow you to add 8 different large-scale plugin solver engines that you can use to extend the power of these products. These make it practical to solve very large problems, essentially only limited by memory. And these engines include Groby, Express, Nitro, and so on. You can do much more with our product. We offer a complete solution for any type of conventional and stochastic optimization problem, simulation and risk analysis, decision trees and forecasting, text mining, and data mining. Furthermore, in terms of optimization models with uncertainty, you can solve the problems using chance constraints, recursive decision variables, and robust optimization and stochastic programming methods. This wide-ranging product line empowers you to perform analytics on the web and desktop applications, desktop spreadsheets, also web server and desktop applications in any scale. As we mentioned earlier, many of our customers have found optimal solutions for their large-scale industrial problems worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline offers powerful tools to help you get a better solution by automatically diagnosing your model structure, fixing problems for you, selecting the solver engine, and providing updated information at each step. For instance, one of these features, the guided mode, helped us choose the right engine today. Now, if you are wondering what is the next best step to begin, please register at our website for free if you haven't registered yet. This allows you to access our downloadable user guides, more than 40 example models like the ones we have been showing here today. Furthermore, it allows you to download a free trial at any time whenever you're ready. During this time, you have full technical support. You can ask questions. Just give us a call, send us an email, or use the live chat. Let me show you how you can access the example. So select when you have one of our products installed, click on Help and then choose Examples. And this workbook will open. So to review optimization model, you can either click here and access all different optimization models. To access the examples we reviewed together today, let's go back to, here, let's go back to Overview. There's this button on line 19. There is another set of optimization examples. These are some of the examples that we reviewed today together, like a scheduling, logistic, and production, different finance examples, and so on. And one more resource for you is our YouTube channel. So the address is YouTube, Frontline Solvers. I'm going to share it with you in the chat box with all of you. And if you click on playlist, you can see different like setup short training videos on stochastic optimization. If you scroll down, you can see different information on optimization modeling, and Excel has 5 videos, and we have other like short videos that are available for you for reviewing each feature. And you are welcome to send any questions or comments to me to consulting@solver.com, and I'm going to share my email address with you. Now let's check the questions. Thank you very much. Pierre, if you are still here, so you're asking about why dividing by 10. This was just one example. If you want to check different values, you can either, so let me show you. With parametric optimization, you can have different values. For example, you want to test values for, we choose for 8%, you want to test 8%. 8%, yes, and then let me change the format cell to number, and then increase, okay, and then like for 9%, and then 10%. So if you want to do that, instead of just having a lower and upper bound and then just give a total number of optimization for these 3 values, you can set the number of optimization to 3, and then instead of giving the lower and upper bound, you define a parameter, select the cell, just enter parameter optimization, and for the lower bound, you can select all these 3 values and pass it in the lower bound, and then click OK. And then define the number of optimization 3 to check all these 3 values. So there are 2 ways to do this. So regarding the difference between this solver and a standard Excel, the first thing is the size of your optimization problem. As you pass the limits on a standard Excel solver, you can't solve a model, for example, with more than 200, I think, decision variables. I'm not sure, actually, sorry about that. But that's one. And then this parametric optimization, you can have access to our more advanced engines that we have here that are available in our product level, these product levels. And then with platform products, you can access extra engines. For example, if you have a larger scale engine, a larger scale problem with millions of decision variables and constraints, you can use our larger scale engines. For example, this LSGRG engine can solve nonlinear problems. For premium solver platform, you can see the engine limits are down here. Variables 1000, constraints 1000. If I go to LP quadratic engine for a linear problem, this engine allows you to solve problems with up to 8000 variables and constraints. And so on for other like evolution for solving non-smooth problems. These are the limits that are available. And also different features about report charts, get data if you want to bring big data, publishing your models, parametric optimization, and so on. So yes, there's a big difference. If you have a real industrial application, we really recommend you to use one of the advanced products. And there are different levels, Premium Solver Pro, Premium Solver Platform. So you can contact our sales manager, Dwayne, and use this number. This is a specific number for this webinar attendee, 775-832-0123. This is just for this webinar attendee, so you can contact Dwayne and ask more questions about different product levels. I hope this helps you, Vasil, if I pronounce your name correctly. If you have any other questions, please type them to the chat box. Again, you're welcome to send me your questions, comments to consulting@solver.com. I really enjoyed presenting this webinar to you, and I trust it was helpful. We look forward to future webinars with you, and we appreciate your time. Bye for now. Bye, thank you.